In Module 4, we're going to see how can we use Monte Carlo sampling to evaluate failure probabilities. So just a quick reminder, when we talk about X, this is going to be a vector of random variable involved either in the definition of our loading or resistance model. We're going to have f of x. This is going to be the joint probability density for our vector of random variables. We're going to have g of x, or limit state function, defining a positive value in the survival domain, negative in the failure domain. And we're going to have omega, or failure domain. So all the values x, such as our limit state function is lesser or equal to 0. So here we have our joint PDF or our marginal PDF for our two variables. We have our limit state surface, so the point where g of x equals 0. And we can represent those on that contour plot as well. We have x1, x2, or two random variable, at least their domain. We have our failure domain here, our domain omega, the joint probability density, and we have our limit state function represented in kind of purple here. So the problem, what do we do in terms of the probability of failure estimation when the number of random variable is much larger than 2? It's not anymore possible to visualize that joint density, and it's not possible to easily integrate in a large number of dimensions. So in those cases, we need approximation to these integral we need to solve in order to evaluate our probability of failure. So we can do this with many methods. The one we're going to see here, or the first one, is going to be using numerical integration using Monte Carlo methods. So basically what it boils down to is to take sample from our joint probability density representing all the variables, and we can represent those samples by the points taken here. And what we're going to do is that we're going to look at the fraction of those samples falling in our failure domain. And the ratio between the number of points falling the failure domain over the total number of samples will estimate our probability of failure. Okay, this is the general idea. We're going to dig into the detail of that method in this module 4. So we're going to look at, in general, how does Monte Carlo integration is defined. We're going to look at an example with a log-normal variable. We're going to look in general, how do we generate those samples that we're going to use in Monte Carlo sampling. We're going to see the example that's going to be tailored for reliability estimation. So using the Nataf joint probability distribution, how do we take samples from such a distribution? We have to be careful. There's some severe limitation with that plain Monte Carlo sampling we're going to see in that module. We're going to cover those limitations so that you don't get caught in using it when it's not appropriate. So this is our first module where we're going to estimate the probability of failure using the Monte Carlo method. This is a very general method, fairly easy to understand, so that's why we start with this one. We're going to see more advanced ones later on in module 12 with these importance sampling. So Monte Carlo, we're going to see in a general way, what is a numerical integration method, such as Monte Carlo? How can we estimate the uncertainty associated with these numerical integration methods? How can we estimate the probability of failure using Monte Carlo integration? And finally, what are the specific properties of these numerical estimators? So first, let's approach Monte Carlo integration through this simple example. So let's imagine we want to try to use Monte Carlo sample in order to evaluate the area of our circle. This is a good example because we know what is a theoretical result, okay? PR square. We know what should be the area of that circle here. But we're going to see if we can approximate that same area with samples. Okay, for that we need to first define our problem. We're going to have a circle of diameter 1, so radius 0.5, defined by this following classic equation. Then what we're going to do is that we're going to define an indicator function. So I denote that indicator function. That is function of x and y, so the two coordinates, so horizontal and vertical coordinate x and y. So we're going to say that my indicator function takes a value 1 if I'm within the circle and 0 otherwise. So I can evaluate the area of my circle that is encapsulated in my unit square by the integral of my indicator function weighted by the probability density that is uniformly defined over my X and Y domain. So this is equivalent from what we saw in the revision model at the expectation of my indicator function that takes as input random variable X and Y over my domain here. So let's do this. So let's evaluate the area of the circle using samples. So if we generate those samples following a uniform distribution in that unit square with uniform probability density, we can evaluate that area P as the expectation of my indicator function. So it represents in the limit where I have access to infinitely many samples, 1 over m, the sum of the values of my indicator function. 1 if I'm inside a circle, 0 if I'm outside. This is exact only if m equals infinity. In practice, we're never going to have access to infinitely many samples. So that's why we're going to rely on the finite set. So this is why this is an estimator, so that this is approximately equal to my area. So we're going to try to do first a fairly limited number of samples. We're going to use m equals 100 samples. So in that case, we're going to see in the example I've plotted here, 80 of those 100 samples are within the circle. So my estimator for my area of the circle is 0.8. Whereas if I compute the exact formula, PR square, I'm going to have 0.785. So I'm close to it, but I'm not exactly on it. What if I increase the number of samples? If I take 1,000, so I'm going to have 759 that are within the circle out of 1,000. So the estimator for the probability of the area of the circle, sorry, the estimator for the area of the circle is 0.759. I'm closer to the true value. If I increase to 10,000, 784 versus 785, I'm getting onto it. So you can see here from the example we just did that the quality of my estimator depends on the number of samples taken. And the big power of that Monte Carlo integration is that the quality of the estimation is independent of the number of samples, the number of dimension I'm trying to integrate into. So instead of having a 2D circle, I would have a 2D sphere. Calculating the volume within that sphere would be independent of the number of dimensions of my sphere or of my hypersphere. So let's look a little closer at this. So let's go back to the case where we're only using 100 samples. So if I generate a first set of 100 samples, I could have, like in this case, 82 points within my circle, leading to an estimation for my area of 0.82. If I draw another set of 100 samples, a different set, this one I would have 73 points within my circle, leading to an estimator that is slightly different, in this case 0.73. And if I repeat this sequentially for a large number of draws of 100 samples, so in total I've drawn 10,000 set of 100 samples. And what I want to show you here is what if I display a histogram of the estimated area of my circle for each draw. It would look somehow like this. You can see that the real pi r square is here, and you can see that there's a spread around that true value. Why? Because I only use a small number of sample in each of those draws. Okay? And what we're going to see is that we can model that theoretical distribution that will define, according to the number of sample we have taken, how much uncertainty we have in the integration we want to approximate numerically. So to do this, let's look again at our indicator function I. That's now going to be modeled by a random variable z. That's going to be a Bernoulli random variable, so that we can model the probability density as the probability that we're trying to estimate. So in this case, it would be the area of the circle, power z, the outcome of that random variable representing my indicator function, and 1 minus p, the complement of the area, power 1 minus z. Okay, where z here can be between 0 and 1. So if we represent this, this is the probability that z equals 1 equal p, the probability that z equals 0 equals 1 minus p. So the probability density, the area of the circle estimated using Monte Carlo will be given in our case by the beta distribution that we saw in module 1. Okay, so if we want to model the probability density for the area we compute using Monte Carlo sample, is then going to be modeled by the beta, where we add that same Bernoulli on the denominator. We simply have our normalization constant, which is the beta function on the denominator. Okay, all this is the beta PDF. They describe a p that is between 0 and 1. And remember, from what we saw, we can interpret the parameters of our beta distribution as the number of outcome. In this case, the indicator function equal 1, so a sample within the circle. And b, the number of time the indicator function is 0 outside the circle. So now, say for instance, if I have 100 samples in this here, I have 84 samples that are within my circle. So A is going to be 84, B is going to be the complement 16. If I plot my beta distribution for A or alpha equal 84, B equals 16, I'm going to get that distribution that describe my current knowledge, given that I have access to 100 samples, 84 of them that are in the failure domain or in the within my circle. That's going to give me my estimator for my probability as well as its uncertainty associated with it. And we can compare this to the reality PR square. If I would draw another set, you can see that I would get like 73. We have a slightly different estimator, but that's still very representative of the reality we have here, another set, another set. Now, if I increase from 100 samples to 1,000 samples, you see how that my beta is getting narrower, okay? But still, it's a good representation of my true value. From one set to another, you see that I can have a different estimator, but that narrower representation of my probability density is still representative of the true value. If I increase to 10,000, you see how my probability density collapse on itself. I'm now very sure, I'm not certain, but I'm very sure about what would be my estimator for my PR square, the area of my circle. So this is the essence behind Monte Carlo integration methods. Now, instead of integrating the area under of a circle within unit square, we want to use that same methods to compute the volume under the joint PDF that is located in the failure domain, because this is what we want to use in reliability to compute our probability of failure. And in this case, the samples we're going to take are going to be samples from my joint probability density for my random variables. Okay. So my indicator function, I of x, my complete set of variable involved in either the resistance or solicitation / loading model, is going to be the indicator function that gives me 1 if the x falls in the failure domain, 0 otherwise. If I want to compute the expected value for the probability failure estimated here, this is going to be the integral over omega, the failure domain. So what we have in pink here, of my joint probability density given by either contour or the surface here. So this is equivalent to say I'm going to replace my omega domain, so the integration over omega, by the integration over the entire domain x, but where my probability density is going to be weighted by my indicator function. Basically, I'm going to put that probability density equals to 1 in the failure domain, 0 otherwise. So this is equivalent for estimating my probability of failure as computing the expectation of my indicator function evaluated for the random vector x. And this is to say, if I have access to infinitely many samples, this is 1 over m, my number of sample, the sum of the evaluation of my indicator function evaluated for each of my vector of samples. In practice, we don't have access to infinitely many samples, so this remains an estimator that we evaluate with a finite number of samples, but we do the same thing. We sum the values of the indicator function, either 0 or 1, evaluate for each vectors of samples. So now let's look at the properties of our estimator obtained using Monte Carlo. And we're going to look at this through the expectation of our estimator and the variance of our estimator. So we want to see, is our estimator biased and what is the uncertainty associated with it. So to look at, is our estimator biased, we're going to look at the expectation of the estimator itself. So if we took the expectation of what we use as our estimator for a probability of failure, we're going to have 1 over m. So we see that the expectation of something that is constant, we can push the expectation into it. So I'm going to have 1 over m sum of the expectation of I of xi. So in that case, this is equivalent to the expectation of xi. So that means that my estimator using Monte Carlo for the probability of failure is not biased. The second property, we can look at the variance of my estimator for PF, my probability of failure. So the variance of my estimator is going to be the variance of my formula I had to define my estimator. So again, if we look back at what we saw in the revision module, the variance of a function ax plus b, where a and b are constant, is equivalent to a squared variance of x. So b is not involved here because it doesn't multiply, it adds on x, and this is a constant. So in that case, I have 1 over m. This is going to be able to be pushed out of the variance operator. So it's going to be 1 over m squared. So I'm going to have 1 over m squared variance of my indicator function. And in that case, this is going to be equals that sum to m times my variance of my indicator function. So 1 over m variance of my indicator function. And remember, what is the definition of the variance? We can have the expectation of my indicator function square minus the expectation of my indicator function square. Okay, this is the identity we saw that is built in the definition of the variance. And here, since my indicator function only take the value 0 and 1, so 0 squared makes 0, 1 squared makes 1. So identity function square is identity function. And the expected value of my identity function, we saw this is simply PF. So here we have PF squared, so PF minus PF squared, we can simplify to this. So the variance of my estimator is 1 over the number of samples taken, probability of failure that I want to estimate, minus the probability of failure square. And what is interesting to note here is that the uncertainty as quantified by the variance of my estimator is independent of the number of dimensions. Okay, so the number of dimensions in X appears nowhere in here. So the only factor that are going to affect the uncertainty on my estimator for calculating my probability of failure is m, number of samples, and the probability of failure I'm trying to evaluate. So if we want to transform this into an adimensional number, we're going to look at the coefficient of variation for our estimator. So coefficient of variation is the standard deviation divided by the expected value. So if we take the two estimator we've already evaluated, we're going to get the square root of 1 over m pf minus pf squared divided by probability of failure. If we simplify this, it's going to give this ratio. The square root of 1 minus my probability of failure divided by m times probability of failure. So in that case, if I want to isolate f, I'm going to get this relationship. So what does it allow me to do is say, if I want to estimate a probability of failure that is at a given range, say 10 to the minus 4, and I want to evaluate it up to a given precision as defined by the coefficient of variation. In that case, that's going to dictate how many samples m should I be taking to reach that level of precision for a given probability of failure. And we can not only compute the moments representing the uncertainty about our estimating, we can plot the whole probability density using the beta distribution, where directly the number of instances where your indicator function was 1 is going to be A, number of instances where the indicator function is 0 is going to be B, and you can plot the whole density. So you can see here, for an example, if I have a total of m equal 100 samples, I have 5 in the failure domain. This is going to be the probability density representing my knowledge of what the variability in my probability of failure could be, given that I have only access to 100 samples. And note that the mean and variances we computed previously correspond exactly to the mean and variance of that beta PDF we have here. So these are two sides of the same coin. So let's look at an applied example where we're going to study more deeply the effect of the number of samples we're taking to evaluate the probability of failure. So if we go back to our classic example where we have a bar that's subject to a tensile force, the strength, the resistance of the bar is R, the solicitation is S. So we're going to say that the resistance is modeled by the dimension of the bar. So the width is 10 millimeters, the uncertainty is 2. So we're going to have our resistance model is going to be d squared times f of y, the yield strength, which is going to be defined in this case is 300 megapascal. Solicitation, the mean is 15 kilonewtons. The standard deviation is 5. And we assume here that the dimension of the bar is independent of the solicitation applied onto it. So we define our limit state function as the difference between our resistance model that involves x and the solicitation. So from a theoretical perspective, we can represent or we can define the probability of failure as the integral over our joint density for D and S over our domain omega, the failure domain that is defined by our limit state function. So if we would be to compute this integral exactly, we would get roughly 0.0838 as our probability of failure. So in that case, if we want to evaluate to what extent we can approximate this result using Monte-Carlo sample. So let's do a very naive approach of taking just 10 samples. So we can see here we have our joint probability density, the same representation with a contour. On the bottom left graph, we have as a function of the number of samples taken, what was our estimator for the probability of failure? So right now we're at 10, but we see we plotted this result as we were drawing samples. And on the right, we have our coefficient of variation associated with our estimator as a function of the number of samples. Right now, you see it's very high. Why? Because we have a very low number of samples and very few of them are falling in the failure domain. So for 10, I have 2 of them in the failure domain. So that gives me an estimation for probability of failure of 0.2 with a very high 0.65 coefficient of variation. So this is clearly not enough samples. Then because I know that the reality is 0.838. So if instead of taking 10, I take 100, now 13 of them are in the failure domain, leading to a 0.13 estimator for probability of failure. Coefficient of variation is 0.27. This is still fairly high, but you can see the evolution of our estimator as we draw samples. The reality is that red dashed line. So we're going to it, but we're not onto it yet. The quality of our estimator as measured by our coefficient of variation is dropping, but it's still fairly high at almost 0.3. If we go from 100 samples to 1,000, you can see that we're going towards with 0.790 toward our correct value, but our coefficient of variation at 0.11 is still significant. If we go instead of 1,000, we go to 10,000, you can see that now we're asymptotically converging to the true value, 0.0857 versus the reference 0.838. Coefficient of variation drops to 3%. If we go even beyond this, say we take 10 to the power 7, so 10 million samples, 0.838, 0.838. And actually, the value here that I estimated as PF, that is approximate, was already approximated with this number. Okay, I myself generated a large number of samples to use as a reference for my probability of failure. And you can see that my coefficient of variation now is 0.1%. This is more than acceptable for structural reliability context. So now we're going to see, okay, it's nice. We just have to take samples. But how do we take these samples? Or do we generate these random samples from a joint distribution? We're going to see in a general context how do we do this. How all these numbers are generated from a uniform distribution, from a marginal distribution following any distribution. How can we do it for multivariate normal distribution? And how can we do it for the Nataf joint probability density? Okay, so that this is what we're going to be using in the context of reliability estimation. So the 4 cases we're going to cover first is going to be the uniform PDF, any marginal PDF, the joint normal, and as I said, joint Nataf random samples. So every random sample, any random sampler starts from samples of a uniform distribution. So something that is equally distributed between the range 0, 1. So what we're going to do is that we're going to use a recursive random number generator. Okay, there's many different formulations. This is the simplest one, just to show you conceptually how it works. So we're going to say that we're going to have a kind of latent space that is not directly observed. This is going to be xi. This is going to be a byproduct of our random number generator. So we're going to have a coefficient a, b, and m. So we're going to take a times x minus 1, the previous xi generated, plus b minus m. We're going to round down to the next integer, a xi minus 1 plus b divided by m. And then our uniformly distributed sample is going to be that xi divided by our constant m. And we're going to do this for a large number. So in this case, a could be, say, 129, b 1, and m a very large number. So in this case, 2 to the power 35. And if we generate a large number of samples, we can see if we draw the histogram for our samples are going to be indeed uniformly distributed. Okay, but keep in mind these random number generation depends on the initial value x0 that you choose. So what it means is that if you choose a given x0 and fixed parameter, you're always going to generate the same sequences of random number. If you plot their histogram, they're going to follow the distribution that is uniform. However, keep in mind this is still a fixed sequence. So this is why we typically refer to these as pseudo random numbers. So if you want to use Python to generate those, np random rand n and m, so a n column and row matrix of random numbers. So now, second case, we want to use uniformly distributed random numbers and transform them into any marginal PDF. Okay, so we have a random variable x that follow that PDF. We want to take samples from it. How do we do? So we're going to use the CDF of that function. And we're going to say the CDF of my random variable is equal to the samples of my uniform random variable. So that's going to allow me to revert that CDF, so taking its inverse. So the inverse CDF of the random uniform sample should give me samples of my arbitrarily distributed PDF X. So if I have here the histogram for my samples that are uniformly distributed for U, if I evaluate those in the inverse of my CDF, the resulting outcome are going to be distributed like the PDF for X that I'm trying to sample from. Okay, this example, I have X that is normally distributed. This is its CDF. I take uniformly random samples, evaluating the inverse of my CDF. The outcome of the samples are going to be normally distributed. So, and I can use this not only for the Gaussian, I can use this for any probability density function. Now, how can I use that the knowledge of my capacity to generate univariate Gaussian distribution or Gaussian samples to generate multivariate Gaussian samples? Okay, so to do this, we're going to first generate univariate Gaussian Gaussian samples, and then we're going to correlate them. So to do this, we need first to make a decomposition of our covariance matrix sigma x into our standard deviation matrix and a Cholesky decomposition of my correlation matrix. So remember, L is a lower triangular decomposition that we can obtain by SciPy linear algebra. We do the Cholesky decomposition of our correlation matrix when we want the lower triangular part. And what we're going to do, we're going to generate some univariate Gaussian random numbers. Okay, I can generate as many dimensions as I want to generate for X, but univariate distribution can be all generated independently. And these random numbers are going to be for a standard normal random variable, so that mean 0 and standard deviation 1, so identity matrix. Then when I'm going to have those samples from Y, the only thing I'm going to do, I'm going to correlate them and I'm going to scale and move them around to represent the mean I want. So how do we do this? We take our samples yi, we multiply by our standard deviation matrix, we multiply by our Cholesky decomposition for our correlation matrix, and we simply add the mean value. So the result are going to be xi, which are taken from a multivariate Gaussian distribution with mean m of x and covariance sigma x. So the key, I remind you, you generate standard normal Gaussian random numbers. You decompose your covariance matrix into standard deviation matrix and Cholesky decomposition of the correlation matrix. And then you're going to scale your standard Gaussian random numbers, and you're going to shift them by the mean. So what is in np.random.multivariate normal evaluated for the mean and covariance matrix is directly that transformation. And finally, the last case we're going to see, how can we generate random number drawn from the multivariate Nataf distribution that is going to be used in the context of reliability theory. So if X is an n-dimensional random vector having a joint Nataf distribution, where we have access to the marginal distribution f of xi, the procedure to generate a multivariate realization from that joint Nataf distribution is first to generate a set of vector zi, which is going to be normal with mean 0 and covariance matrix as R0, the correlation matrix for our Nataf distribution, where R0 are the intermediate correlation for our z's. Then once we're going to have these samples, the only thing we need to do is to transform each of them one by one through the CDF equality function that we have defined with Nataf. So we're going to take this standard normal CDF for the ZIs we generated, inverse CDF for each of the respective XI. And these going to transform the ZI samples in XIs, and I'm going to have access to the samples from my Nataf distribution. So let's look at a practical example of that sampling from a Nataf distribution. So we're going to look at the marginal PDF, we're going to look at a joint PDF, and then we're going to see how can we estimate our probability of failure with such a method. So we have the same configuration as before, but now the x1 representing the dimension of my bar is a log normal distribution. X2, which represents the solicitation, is a gumball, where the joint distribution is represented by a Nataf, where our correlation coefficient is 0.3. So in that case, I'm going to define my x vector as d and s, mx, 10, and 15 as defined by my parameters here. And we're going to have our model for the resistance d square f of y, where f of y again is my yield strength. And my limit state function is the resistance minus the solicitation, and where the resistance is function of x, in this case, d, the dimension of the bar. So we use the relation we saw in module 1 to go from the mean and coefficient of variation for x1 to the mean in the log space and standard deviation in the log space. So this is going to be my lambda, this is going to be my zeta parameters. So I can find these two values for the parameters of my log normal distribution. I do the same thing for my gumball. Remember, gumball is the GEV type 1 distribution. I'm going to have here its PDF, its CDF. I need to evaluate from the mean and standard deviation, the mu and beta parameter. And in order to do this, I need to solve this two equation, two unknown system. If I do it from mu x and sigma x, I want to evaluate mu and beta that are going to be solved as 12.8 and 3.9. Now I'm going to build my joint density using a Nataf distribution. So I'm going to model my joint PDF between my log normal and gumball as the bivariate standard correlated PDF, standard normal PDF, times the product of what we have here, the marginal probability density for xi divided by the marginal probability density for zi. I need to define in that R0 what is my correlation coefficient in that standard normal space. So I take my original correlation coefficient, 0.3, times this equation that is defined from the two marginal distribution. So log normal and gumball for these two. That is function of the parameter of those two marginal. That's going to give me a correlation coefficient of 0.31. That is very close to the 0.3 I initially had. So my R0 that I'm going to reuse here is 11.31 on the off diagonal term. And my transformation function to go from my z space to my x space is going to be the standard normal CDF of zi, the inverse CDF of my log normal, and my second one, the inverse CDF of my gumball. So if we look, how can we do this using Python? So we are going to need the SciPy package, the multivariate normal, NumPy as NP, standard one. So I can build myself some lambda function to transform the parameters, say, um, of my log normal random variable. So when I do this, I can evaluate numerically these values. So once I give these values as input, I can evaluate my inverse CDF for the log normal using the norm CDF of Z1. So this is a generic lambda function to transform from Z to X1. I have a second one from Z to X2. In this case, the inverse CDF of the GEV with the mu and beta that I've obtained previously. So it means I'm going to be able to call these functions, so x1tz, x2tz, with input z1 and z2, and that's going to transform me into from a z space to an x space. So then I want to build myself a third lambda function. It's going to simply concatenate these two vectors. Then if I take, say, 10 million samples, I'm going to take multivariate normal random samples with mean, in this case, 0, correlation matrix that is R0. So I assume I'll already compute my R0, and I want to take 10 millions of them. So these are 0 mean and correlated by R0 random samples. And then I simply pass them in my transformation function x dz. So I transform z to x. These are going to be my Monte Carlo sample. And then if I want to evaluate my probability of failure, the only thing I need to do is that I am going to evaluate those samples into my limit state function. And I'm going to make a comparison with 0. So my indicator function is going to be valued 1 if it's lesser than 0, 0 otherwise. And my probability of failure estimated with Monte Carlo is simply the sum of my indicator function divided by my number of samples. Okay, so in a very few lines of code, we can estimate the probability of failure in arbitrarily large number of dimensions. So if we look at, in this case, for 10 million samples, I'm going to have here an estimated probability of failure of 0.049 with a coefficient of variation that is less than 0.1%, so very small. So that's going to be an accurate estimation of my probability of failure. So what are the limitations of that Monte Carlo estimation for probability of failure estimations? So first, it's common that our limit state function involves complex numerical models such as final model represented here. And when the evaluation of one limit state function takes more than, say, 1 milliseconds, or when the probability of failure is much less than, say, 1%, then it's become impractical to evaluate a large number of samples. Because remember, the number of samples we take to reach a given coefficient of variation for a given PF grows really quickly. So if we look at here, if we plot that relationship for PF in the log scale on the horizontal axis, and for the coefficient of variation, say we want to have a coefficient of variation of less than, say, 5% for probability of failure, that is in the order of 10 to the minus 6. The number of items or the number of samples we need here is incredibly high. It's represented here, the same contour that we see here are this plot here, but you see here I truncated the corner because if I would plot it, it would look like this. So it would be an unreasonable requirement in terms of number of samples required. So what do we do when we have a limit state function that takes a substantial number of seconds to be evaluated, and we want to evaluate very small probability of failure? So in this case, we're going to see in module 5 to 7 the analytical methods to do such integration using FOSM, form, and SORM. And we're going to see in module 12 the more advanced sampling methods, such as importance sampling, directional sampling, ASAR. There are many methods that can be used in order to speed up the Monte Carlo sampling while having an accurate estimation. So in summary, the Monte Carlo integration allow us to easily estimate our probability of failure numerically by representing the probability of failure as an integration, or in this case, the calculation of an expectation. So we're going to have our indicator function, and we're going to simply compute the average of that indicator function that can either take 0 or 1 as value. We saw that the variance of our estimator is independent of the number of dimension. It only is a function of m, the number of sample we take, and pf, the probability of failure we're trying to estimate. So if we revert that relationship, we can define for a target order of magnitude for a probability of failure, say 10 to the minus 4, in our coefficient of variation we want to reach, say 1%, we can add a target number of sample that would be needed to be taken. If we want, we can draw the complete probability density function representing our current uncertainty about our Monte Carlo estimator by taking the alpha and beta parameter of the beta distribution, where alpha would be the number of instances of my indicator function being 1, beta the complement. Number of instances where the indicator function is 0. And the main limitation of the Monte Carlo methods we saw here, we could say this is a crude Monte Carlo method because it requires a very large number of samples. And in practical cases where the number of the time required to evaluate our limit state function is fairly large. So in terms of seconds, we're not going to be able to take millions or tens of millions of samples of our limit state function. So if we're in that bottom left corner where we require a very large number of samples, this crude Monte Carlo method is not going to be sufficient anymore. So we're going to start in the next module looking at the analytical failure probability estimation method using FOSM, first order second moment methods.